got an interesting challenge up our sleeves. Now, when you're looking for a challenge in programming, sometimes you gotta look towards, in very strange places. So I was thinking, I want to eventually build some kind of, like, music or rhythm game engine or something. But to do that, I need some kind of format to play music in. Now, I've done a like rhythm game like engine, a really fast one, before, and what I did was I used like a pseudo MIDI file format where I created like notes to the beat of timed like placement of notes based on like MIDI. But I didn't actually read a MIDI file. All I did was emulate a MIDI file by looking at the sheet music and then programming in the notes. I was thinking today we could try something a bit more interesting, and not just today, because I've never done this before, but over probably the next couple days, we're going to try implementing a MIDI file reader. Before I get too far into this, let me show you the sample file we're going to be using. It's a tune I am familiar with. It's actually from Toho. This is Gensokyo Millennium, History of the Moon, which is from Toho Imperishable Night. It is one of the boss themes. Final boss theme, actually. So yeah, that's a little taste of the music itself. Now, how do we go about interpreting a MIDI file format? We're basically gonna make something that will interpret the file format for us to create a rhythm game engine with. Now, why might I be doing this? Well, the MIDI file format is great because unlike, I guess you could call it like analog music, or like this music is certain notes pressed at certain times, dictated by the chart itself. So it's perfect for developing like something that requires timing, because you already have the notes and the times, and it's a very flexible format. But I thought to myself, why not try and implement our own instead of using something that's already out there? It's a lot more fun to develop things yourself, and it could be kind of cool to learn about these things. So I think this is going to be a very educational endeavor. It might take a couple days, and we're probably going to learn a lot. I've never done this before, but I hope you guys will enjoy the journey getting there. So let's first just take a look at what a MIDI file looks like raw if we were to just open it up. I have it stored inside of here, but I'm gonna have to move it. I just put it in here because it was in the same repo. So I'm just gonna open it up in Notepad++. So you can see here, there's a lot of like visible letters, and then there's a lot of these like null characters. The null characters probably represent like zeros, but then there's like other characters too. These are all like binary characters that can't be rendered normally, so in Notepad++ they show up as all these weird like system codes. In any case, we're going to be interpreting this entire file. So I just took a look at this. This looks like a very good documentation of the standard MIDI file format spec. Whenever you're dealing with reading a new file format, you're going to probably have to familiarize yourself with like bits or bytes. So let's just take a quick little read here. It contains the detailed structure of MIDI files. MIDI files provide a way of interchanging time-stamped MIDI data between different programs, so that's why it's a very flexible format. MIDI files contain one or more MIDI streams with time information for each event. Song sequence and track structures, tempo, and time signature information are all supported. Track names and other descriptive information may be stored with the MIDI data. The specification defines the 8-bit binary data stream used in the file. So it's an 8-bit binary data stream. That probably means we're going to be dealing with bytes. The data can be stored in a binary file, nibblized, 7-bitized for efficient MIDI transmission, converted to hex ASCII, or translated symbolically. Yep, depending on what the program's trying to do. In this document, bit 0 means the least significant bit of a byte, and bit 7 is the most significant. So if you're thinking of a number, the most significant digit is always the one on the left, right? So bit 0 will be on the right, bit 7 is the one on the left. So in a byte here, you have 8 zeros. So 1 byte is equal to 8 bits. Some numbers in MIDI files represent in a form called variable length quantity. These numbers are represented 7 bits per byte. The most significant bits first. All bytes except the last have bit 7 set. The last byte has bit 7 clear. If the number is between 0 and 127, is thus represented exactly as 1 byte. Interesting. To any file system, a MIDI file is simply a series of 8-bit bytes. On the Macintosh, this byte stream is stored in the data fork of a file or on the clipboard. Most other computers store 8-bit byte streams in files, like the one we have here. MIDI files are made up of chunks. Each chunk has a 4-character type and a 32-bit length. Okay, chunks. 4-character type, 32-bit length, which is the number of bytes in the chunk. The structure allows future chunk types to be designed, which may be easily ignored if the program written before the chunk type is introduced. Each chunk begins with a 4-character ASCII type, followed by a 32-bit length. So an ASCII type means it's probably going to be representing actual letters. We vaguely saw this here. I can see there's like MTRK, MTHD, FPCF, like I see all these, right? They all represent something. We don't know what yet. It's followed by a 32-bit length, most significant byte first. This length refers to the number of bytes of data which follow. The 8 bytes of type and length are not included. Therefore, a chunk with a length of 6 would actually occupy 14 bytes in the disk file. MIDI files contain 2 types of chunks. Header chunks and track chunks. Oh, look at that, MTHD. A header chunk provides a minimal amount of information pertaining to the entire MIDI file. A track chunk contains a sequential stream of MIDI data. A MIDI file always starts with the header chunk and is followed by 1 or more track chunks. Okay. MTHD, length of header data. So I'm guessing all these probably represent those things. So we're gonna find out what these are in a little bit here when we start writing some code. So yeah, let's do a little bit of project prep. Let's open Eclipse here. So how would we read this file? Well, since we got a bunch of these characters here, it's probably better to interpret this file in binary. Now, binary file reading is a little different from string text reading, because instead of interpreting everything as a character, we're going to interpret it as a byte. So a byte holds 8 bits, which means it can be anything from 0 to 256 and represented as such, a number. I'm going to call this project MIDI reader. Pretty appropriate, right? I just created a class, my bad. Delete, undo. How do I, really? New project, please. MIDI reader. I really need to hit don't create modules. I always forget to do that. Alright, so let's get our project started. We'll put this in the SIG package yet again. And create a class called the MIDI reader, which will be our main class. We'll hold our main class. As always, start with our string args and go from there. Now, first thing I'm going to do is import my utils. Why? Because I'm going to do some file reading. And I have a nice little utility function inside file utils called read binary from file. And you guessed it, this file will read binary instead. Taking a look at the code real quick, unlike this, when we open a file stream, we're going to grab all the bytes by just reading every single byte. So doing input stream.read reads byte, and we've specified the size here by reading the length of this file, which is going to be defined by how large it is. So we specify the file name, reads the file size, that's how many bytes we read in. All the bytes get stored and returned as a byte array. Pretty easy for us. Kind of like the, excuse me. File utils is probably not imported yet, so we want to import that. Let's do this first. Data, file utils, read binary from file, and specify a string. Kind of like our read from file function, but it's going to read binary. So our file, again, we have to move it to the right repo. Put in our root directory here, and we'll copy paste the file name. So that should read our data, so then we can print it out. We're just printing it out for the sake of seeing what the data looks like in here, because we already saw that inside of our Notepad++, we saw all these weird characters, right? So let's go ahead and run this. You'll see, unlike when we saw it in our Notepad++, we just have a bunch of numbers. These numbers are all values between 0, well, actually, any numbers between 256, or excuse me, negative 128 to negative 128? Yeah, to 127. I think, or negative 127 to 128. You might be wondering why. Well, the main reason is because this is probably assumed to be signed. So if we assume this is unsigned, I don't even think you can make unsigned here, but that's how they're interpreted. So negative actually stores, I think, the last bit, makes it negative. I think that's how it works. So you have the numbers like, you have bits 0 through 7 or 6, which represent the number itself, like 0 through 128, and then you have one bit which represents negative. So I think it works somehow like that. But since these numbers are kind of annoying to read, not only are we going to include the numbers, but let's also include a human readable version of each byte, because I think it would be nice to have that. So how do we do that? Well, we have to output not only the byte, but the character it represents. So I think it would be pretty cool to have those side by side, don't you? So instead, we will output a very, very long amount of data, starting from with the byte, and then a few spaces, and then a character casted version of our data. And I think this would be a better way to represent what we're looking at, because we get some human readable characters next to our numbers. And if we want to, we can actually insert a tab here, because a tab kind of lines things up for us. I think that'll make it a little more readable. Alright, I think one tab was good enough. I didn't have to do two. There we go. So you can see now we have numbers followed by the letter it represents, if there is one. So you can see we kind of have a better picture now, because unlike in this, at least we couldn't see these numbers that were after it before. So now we kind of do. So as we go through our file and start reading it, we can kind of follow along with these letters, because they're printed out characters. So that's gonna be helpful. So I guess we should just get started then. It says the header chunk at the beginning of the file specifies some basic information about the data in the file. Here's the syntax of the complete chunk. Header chunk is chunk type, length, format, number of tracks, I'm guessing, and division. As described above, chunk type is the 4 ASCII characters MTHD. So there's MTHD right there. Length is a 32-bit, so it's after chunk type, 32-bit representation of the number 6, high byte first. So, what this means is that we should see the next 4 bytes represent this number. So a 32-bit representation of the number is 4 bytes, because 32 divided by 4 is, or 32 divided by 8 is 4. So the next 4 bytes represent the length, and it says the high byte is first. So that means that we kind of read it from left to right, like normal, right? So if the high byte is the most significant digit, the last byte is the least significant. So 1, 2, 3, 4 here. You can see this does represent the number 6 if we put them all together. 00006. Or 0006. So that is true. It's the number 6. Why is it the number 6? I don't know. I guess they chose that number. The data section contains 3 16-bit words stored most significant by first. The first word format specifies the overall organization of the file. Only 3 values are specified: 0, 1, or 2. Let's take a look at that. They're 16-bit words, so we should expect 2 bytes per word. So we do indeed see a 1 here. That means the file contains 1 or more simultaneous tracks of a sequence, which I think makes sense because we did hear multiple tracks playing at the same time. At least on this piano, I think it was a left hand and a right hand. More information about these formats is provided below. So I'm not going to write any code to actually interpret this file yet, but we're just going to keep going and reading about what we need to look for. Because what's important to us are the actual note data. We need to grab the note data, and then we need to be able to play music with that data. That represents the music stored in this file. The next word, number of tracks, is the number of track chunks in the file. It will always be 1 for a format 0 file. So number of track chunks. It says 2, so I guess was correct. There were 2 tracks. The third word, division, specifies the meaning of the delta times. It has 2 formats, one for metrical and one for time code based time. Alright, let's see. So, again, 2 or 16 bits. So, if bit 15 is 0, then all the bits represent ticks per quarter note, whatever that means. Or if the bit is 1, it represents a negative SMPTE format, and bits 7 through 0 represent ticks per frame. So if bit 15 of division is 0, the bits 14 through 0 represent the number of delta time ticks which make up a quarter note. For instance, if division is 96, a time interval of an eighth note between 2 events in the file would be 48. Alright, let me think about that for a second. So it represents how many ticks make up a quarter note. So if division is 96, an eighth note is 48. So we don't know where we get the delta time ticks yet. Or wait, or is that what that represents? Let me see what we got here. That'll probably paint the picture for us better. So we have a 1 after this, so it's using that other format. So it says negative SMPTE format. If bit 15 of division is a 1, delta times in a file correspond to subdivisions of a second, in a way consistent with SMPTE and Midi timecode. Bits 14 through 8 contain one of the 4 values, negative 24, negative 25, negative 29, or negative 30, corresponding to the 4 standard SMPTE and Midi timecode formats. So we probably have to do research on that because I don't know what those are. Negative 29 corresponds to 30 drop frame and represents the number of frames per second. Let's see what we have here. So we have bits 14 through 8. Oh, it just says negative 32, like literally. So negative 32... Wait, am I reading this right? Hold on. So we have a 1, we have a 2, then we have a bit 15 that's set to... Wait. No, that means bit 15 is a 0, right? Because if that's a 1, it represents a 0, so bits 14 through 8 is a negative SMPTE format. Oh, these negative numbers are stored in 2's complement form. The second byte is the resolution within a frame. Typical values may be 4, 8, 10, 80, or 100. Wait, so is this the third word? This is the third word, right? Okay. So am I reading this backwards, or am I reading this right? I can't actually... let's see. Let's, first understand. Okay, let me see. The positive sign bit is, on the left. Okay, that makes sense. If the sign bit is 0, this means the number is positive in value. If the sign bit is 1, then the number is negative in value. So that would be the first bit. So bit 15 is the most significant bit, which is on the left side. So in this case, if we were to actually represent this in binary, I guess it would end up being 7 zeros and 1. Wait, let me write that here or something. Like that. And then negative 32 would be a 1. And then 32, so that's 128, 64, 32. Wait. No, that wouldn't be right. This would start at 64, then 32, followed by zeros, like this. So this is what it would actually look like for a 1 and a negative 32, I believe, because this would be... This number can only store up to 127, or up to negative 127, I should say, with the signed bit there. So that looks like negative 32 to me, I think. Because, yeah. So bits 14 through 8 represents a negative SMPT format, but it also says these negative numbers are stored in 2's complement form. So 2's complement, I don't quite remember what that is. In 2's complement form, a negative number is the 2's complement of its positive number with the subtraction of 2 numbers. Okay. Stop. A negative number is represented by a binary number, which when added to its corresponding positive equivalent, results in a 0. In 2's complement form, a negative number is the 2's complement of its positive number with the subtraction of 2 numbers being a minus b equals a plus 2's complement b, using much the same process before. 2's complement is 1's complement, plus 1. Huh. The 2's complement of 27 will be 111000101. Because subtraction then results in just flipping that. Or, oh, because you add them together. I see. So the second byte, stored positive, is the resolution within a frame. Bits 7 through 0. So what value do we have then if it's this? Because right now it says it's -32, but that can't really be right because it's stored positive. So if it's stored positive and it's represented as this, that means it's 128 plus 32? Would that be 160? Interesting. So I feel like this is gonna be a little tricky to figure out later because this is gonna represent how our timing is. A format 0 file has a header chunk file by 1 track chunk. A format 1 or 2 file has a header chunk file by 1 or more track chunks. Programs which support several simultaneous tracks should be able to save and read data in format 1 as a collection of tracks. All MIDI files should specify tempo and time signature. If they don't, the time signature is assumed to be 4/4 and the tempo 120 beats per minute. In format 1, these meta events should be contained in the first track. I assume the first track starts after or something? Maybe? M track. The track chunks, type M track, are where the actual song data is stored. Each track chunk is simply a stream of MIDI events, preceded by time delta time values. The format for track chunks is exactly the same for all 3 formats. Here's the syntax of an M track chunk. A plus means 1 or more. At least 1 M track event must be present. So track chunk. The syntax is very simple. Delta time event. Delta time is stored as a variable length quantity. It represents the amount of time before the following event. If the first event in a track occurs at the very beginning, or if 2 events occur simultaneously, a delta time of 0 is used. So this is chunk type. Oh wait. Delta time is in some fraction of a beat. Event is MIDI event, sysx event, or meta event. MIDI event is any MIDI channel message. See MIDI messages. Running status is used. Status bytes of MIDI channel messages may be omitted. The first event in each track chunk must specify status. The length is stored as a variable length quantity. It specifies the number of bytes which follow it, not including the F0 or the length itself. For instance, the transmitted message F0 4312, so on and so forth. So this is in hex, which is 240. I guess I should get this out, huh? That might be helpful. 247 will be stored in a MIDI file as F005. Huh. So it specifies the number of bytes which follow it, not including the F0 or the length itself. So if I read in this, it says there are 240 bytes which follow it. Oh wait, no, it's F0 and then the length in bytes, so it would be like 67 bytes. I guess I gotta read the variable length quantity thing again. Some numbers are represented form called variable length quantity. They represent 7 bits a byte. Okay. All bytes except the last bit have bit 7 set. The last byte has bit 7 clear. Interesting. Whoops. Huh. Yeah, I'm just trying to understand the idea behind this. So it goes a number between 0 and 255, but all bytes except the last have bit 7 set. So for the numbers that don't have bit 7 set, you end up with 127. Okay, that makes sense. And the last byte has bit 7 clear. So when we say we're trying to represent the number 3FFF, or even 2000, just a little confused by the number structuring here going on. Because the length of star is a variable length quantity. The variable length quantity tells us how many bytes will follow it. And the variable length quantity goes on until I think the F7 is reached. So the transmitted message F043120007F7 would be stored in a MIDI file as oh, I think it's just telling us how it works, because the 5 represents the number of bytes to be stored. 1, 2, 3, 4, 5 to include, or not including, the F0 or the length itself. So 5 after that. It is required to include the F7 at the end so that the reader of the MIDI files knows it has read the entire message. Okay, that makes sense to me. Another form of sysx event is provided which does not imply that an F0 should be transmitted. Here's the MIDI file of a multi-packet system. Exclusive message. Suppose if those bytes were sent, followed by a 200 tick delay. So is that 200? How does one read that? Hmm. 100 tick delta time is 6.4. Does that just represent like which bits are on? I don't think so. There must be something else to it. So it looks like all these FFs followed by something represent some kind of like metadata events. Which I guess will be represented with like negative 127s, because I guess that's the only way you would get that number, right? A Midi message is made up of an 8-bit status byte followed by 1 or 2 data bytes. Channel messages apply to a specific channel, and the channel number is included. System messages are not channel specific, and no channel is included. NNNN is the MIDI channel number. So will we see these as like negative 127? What about something like this? Here's a negative 125. What is this supposed to be? 1, 2, 4, 8, 16? So 128 minus 16 is 112. Followed by, I assume, like a data byte. Table of MIDI controller messages. Data bytes. Oh, this is hex. Decimal. All MIDI note numbers by octave. Interesting. Names of instruments. So they show some algorithms for reading and writing a variable length value. Contents of the MIDI stream represented by this example are broken down here. Okay. So it says 9/6 per quarter note. I think since ours is format 1, it's going to be a little different. Then the track chunk. Its header followed by the events. Let's have a quick look at what this looks like in here. because this might make it a little easier to read. Because I mean, we saw the same numbers and data in here. Just ring in here, convert to hexadecimal might be a good idea. Could also convert it to hexadecimal on the side here too. That might not be a bad idea. Something to consider at least. So I do see this is where the time signature starts, I presume. And everything before that was the length. Let me see. Because we had chunk length, we had format 1, we also had 2 tracks, and we had this like negative number here. So that all kind of comes with its own format, which I was reading was its own thing. I don't think we should worry about that right now, though. So would this represent the time signature then? Kind of looks like it would. I forgot to read this, but I assume this was 4-4. Time signature. That was like way up here. Five 804, then NNDDCCBB. So all of this. This time signature expresses 4 numbers. NN and DD represent the numerator and denominator of the time signature. The denominator is a negative power of 2. The denominator is a negative power of 2. What? Two represents a quarter note, 3 represents an eighth note, etc. Oh, so it's a negative power of 2, as in the larger it gets, the smaller the value it represents. The CC parameter expresses the number of MIDI clocks in a metronome tick. 1/8. (24). The BB parameter expresses the number of notated 32nd note in a MIDI quarter note. 24 MIDI clocks. So 24 MIDI clocks in a metronome click. The number of notated 32nd notes in a MIDI quarter note, which is 24 MIDI clocks. So that would be 8. 8 30-second notes in a 24 MIDI clock. 8 noted 30-second notes per quarter note. I see. Okay. I don't think that's significant for what we're trying to do, though. Time signature doesn't matter too much. "24 MIDI clocks is 1 crochet, 1 beat. 8 30-second notes per 24 MIDI clocks." Yeah. That's actually the same one we have. So then we have how fast it is. So the next is the tempo. So I'm guessing it's always going to be the delay, so 0, then the value itself. So FF and then 5/9. 3 bytes. So yeah, 5/9 is represented as 89 in decimal. Wait, how do we get this? Oh, it's... Okay, it's 3 bytes. So take the bit here, which is... Oh, wait. Yeah, so we have to take one of these. I mean, if it's FF, then we have to take 128, right? Am I missing something here? Because 5/1 is only 81. Unless I'm missing something here. So I kind of forget where this goes to. Nope, we're not doing that. Why is this in Korean anyway? Oh, here. Wait. Interesting. Wait, what? Why is it not? I'll see a place to actually change it. Oh wait. No, it was right at the top. I was just blind. First the header chunk, then the track chunk, followed by these. Tempo, which is all this. FF51 0307 A120. Because it ends up being 51, right? Which is or let me see, 03 7A120 FF51 is the event code. Okay. So FF51 represents tempo, which I think was probably talked about up here and I just wasn't looking. Set tempo in microseconds per MIDI quarter note. A tempo change, microseconds per quarter note. Representing tempos as time per beat instead of beat per time. Okay. So that makes more sense. It's represented as 3 bytes after the initial code, along with a variable data number that says how many bytes it represents. So this is also like that. It's a variable number too. Because it says it's gonna have 4 values, and then these are the 4 values, right? Because 4 time, 24 MIDI clocks, and 8 30-second notes per. Okay, that makes more sense. That value was confusing me. So FF51 represents tempo, followed by 3 bytes here. So starting from here, 24-bit integer is 3 bytes, so this is the, I guess this is, is that 12 million? That doesn't sound right. That's because it's supposed to represent how many microseconds per quarter note? Is that nanoseconds? I think that's supposed to be nanoseconds. So that doesn't sound right to me, at least not initially. Unless I'm clicking the wrong number. Let me type it out. Okay, that number looks a little better. 198,072 per quarter note. That would be how much time? So I think that's our first real like big piece of information, the tempo, right? Extracting the tempo from it. That does sound a little fast though. Like not like ultra fast, but it does sound fast. So if I do 1 million divided by whatever that is, (0305B8), which is 198,072. And I do 1 million divided by that. No. I end up... It's not exactly 5, but it's gonna be around 5. That sounds like ultra fast though. 300 beats a minute? Yeah, that sounds too fast. So I wonder... Oh wait. Here's the tempo, okay. These. But that's a larger number, ain't it? Well, I guess a larger number is good. It means that the actual delay amount is going to be larger. 05B8D8. The 3 represents the size of the variable. Okay, 375,000. That seems a lot more manageable. Divided by 375,000. Okay, so this is... That's not correct. Let me use decimal precision here. So 1 million divided by 375,000 is 2.66666 multiplied by 60. Gives us a tempo of 160 beats per minute for this song, which sounds correct. So, metronome. Let's just listen to it real quick. Dun, 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 dun. Dun, 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 dun. Bum, 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 bum. Yeah, that sounds about right. Alright, so it looks like we can extract that value that way. So I think that's going to be our first real big piece of data we're going to need, because we need the tempo to know how fast we need to hit the notes, right? So, in terms of all the rest of the bits, we can kind of skip them a little bit, at least down to where we need to go. So navigating this is going to be a little complicated, but basically we know once we hit the track data, the first set here, so this actually represents FF, doesn't it? Or am I wrong? Because we have MTRK right here, 0, 0, and then we have 5, 8, and 4, 9, which are right here. You know what? I really should have hexadecimal in here, shouldn't I? Let's see if we can get that real quick. I think to convert to hexadecimal, or at least display hexadecimal, we just have to format it a certain way. So if I go ahead and do... I feel like there's a string formatter for this. Let me look it up. Format string hex. String.format. Format. So I think we have to supply like a %6. Wait. %05. What does that mean? X. Oh, that's hexadecimal. Okay. The width used in format is always a minimum width. Oh, I see. So we put the amount. So we do 2, because we only need 2. X is for the hexadecimal. Provide the data value. And then it'll be converted to hex, I think. Does that look right? Yep, sure does. We have 4 delta, 5 4, 6 8 6 4, bunch of those going down here. So yeah, that looks good to me. That's in hexadecimal indeed. So that'll help us match up what we're looking at here and what we're looking at over here. So we do want to get down to MTRK, and then we will skip down to FF51. That's actually what we're looking for here. So we're gonna go straight for this. So until we find this sequence of bytes, we're just gonna keep going, I guess. So we'll do some file seeking here. We're looking for a -1 and an 8-1. So to finally start off our program, let's grab the tempo. I guess the tempo can be represented in like a double or something, because it could be a decimal value, but it's probably not going to be a decimal value because it's going to be represented in nanoseconds, actually, now that I think about it. If we represent it in nanoseconds, nanoseconds per beat. How about that? That sounds better, right? Because... 1 second is a million, so if we have a number like 375,000, we just keep adding to that until there's a difference of that much, and then that's 1 beat passing. So I think that makes sense to us to keep nanoseconds per beat. Represents the tempo. Actual tempo is 1 million divided by nanoseconds per beat. Cool. So we're gonna seek, actually I need to keep this is our debug output. Seek the tempo. Seek to the tempo first. So we're going to have to go through our byte array, and we're gonna need a pointer. So we're gonna have a pointer. Start at position 0 and increment it while data pointer is not equal to, what values did we say? We said -1 and 81. And data pointer is not equal to, or +1 is not equal to 81. Pointer ++. Read the next, let's see. So the tempo itself is going to be inside of whatever the size of the next byte is after that. So we'll call this, we'll store it as a long, I guess. Yeah, so we'll store nanoseconds per beat is equal to get long data, starting from data, starting from pointer, I guess. Get long data variable length. So in order to read this, we basically read the length of the bit. So length will be equal to data pointer plus, let's see. So we put the pointer at where this is -1 and this +1 is 81. So we're going to add 2, I guess. +2. Yeah, and that puts us where we want to be. So the length is actually going to be at data pointer. Or do we want to just do it this way? I think this way is better. It's more intuitive this way. So we'll add 2 to pointer, get that value, and that will be our length. Then we read all 3 of those values and mush all the bytes together. So for int I is 0, I is less than length, I ++, we will have a long representing, also we're returning a long here. So we'll just store it as value. Value starts at 0. And then for each pointer along there, we're going to actually do a bit shift over and then adding the values. So bit shifting, how we do that is by taking all the values, and if we bit shift, I think to the left, we think, because we're going towards more, no, if we bit shift to the right, then we get more place values, I think. If we bit shift to the left, we get the values increasing. So we always want to bit shift to the right to make room for more values coming in, I think. We'll find out. So bit shifting is where you take all the bits and you just move them over a certain amount across so that you can insert more values where the original bits were. So if we were to create our example here, we would start from We would create our values, then we would bit shift them all to the right or left. I'm trying to think how this will be. No, if we bit shift them to the left, that will mean we're increasing the value in that regard. We can do it in reverse, I think. So we can start with the max and then bit shift everything that way to add more afterward. I think that's doable. Let's try that first, because I think that's the best way to do this. So value equals value bit shifted 8 bits over added to data pointer plus I, like so. Then we return value. So ideally we want to end up with the correct number here. Let's see what this gives us. Nanoseconds per beat. I'm just gonna run it. I think it just outputted 0. Nice. So nothing was there. Well, found at position pointer. So it says found at position 23, which I think is correct. So this is 20. 1, 2, 3. Wait, is this 20? That's 8, 16, 24. That doesn't sound right. Because this represents, yeah, this is 16. This is in hexadecimal. So this represents 16. So by the time we get down there, is there another spot where that can be true though? I don't think so. Let's see a traverse do this real quick. See what we're looking at here. Dang it. This isn't JavaScript. Also, we're running out of time, but we'll end it soon. So it is indeed going through this. Actually, it does look like -1 and 88 are pretty close by. Oh, but I'm looking at the wrong things. Whoops. I want -1 and 81. My bad, my bad. So we want to go all the way down to here, actually. FF51. -1 and 81. Wait, what? That's what I'm doing, right? -1. 81. Negative 188. Why is that 88? Oh wait, we have to do an OR statement here. Okay, my bad. Faulty logic. There we go. Now we're at the right position. Now we have to figure out why this is still 0. So get long data variable length. So for each of these, we'll read in what data pointer plus I is. Make sure we're getting the right values there first, because it should be reading it backwards. So it's 5381, and then, so clearly, yeah, it's 5381 backwards. 5. What? Oh, it's reading the wrong numbers. It needs to start 3 after. Oh, so add 2 to the pointer, first of all. I'm just gonna do plus equals 2 here, so I don't keep confusing myself. Okay. Alright, so now we end up with this, which still isn't right, but at least we're getting negative 40, negative 72, then 5. Negative 40, negative 72, and 5. Now to compose the numbers together, you just have to write this. You just have to write it, and then I think you just bit shift everything this way, probably. I would imagine. It's gonna be one or the other. It doesn't look like it. Okay. Well. Let's see what happens to value as that gets changed. Nothing really, actually. Nothing changes at all. My guess is these bits are just not being combined together. So maybe, let's just do an experiment. Let's start by ANDing these together, right? Alright, that doesn't change anything. Well, I guess that makes sense because none of these bits are matching. The value is 0, so AND is not going to work. If we OR them together, that's going to give us some kind of value, but I don't think it's going to give us the right kind of value. Because a long is not represented as bytes. So, should we just take each one? Each one needs to be bit shifted a certain amount over, right? Based on where it's located. So just out of curiosity, what happens to our value if we do data pointer plus I, bit shifted over by how far I is, multiplied by 8? Now what about the other way? Aha! Now we're onto something. So basically, these represent the numbers that need to be squished together, in a sense. Although, it's not supposed to be negative, it's supposed to represent like a positive number, I think. So here's the deal, they're supposed to be signed, right? So... although I think when I did this... yeah, they should be unsigned. To make an unsigned byte, we can cast the byte into an int and mask the new int with a 0xFF. Ah, to get the last 8 bits. Java uses 2's complement to represent signed numbers. Oh, okay, yeah. Thus that gives us negative. Only have 7 bits to store numbers, so to do that, we have to do whatever we have convert to an int. So, convert to an int, and that number. Okay. So this didn't convert right. At least I don't think it did. Oh, you know what? It needs to be I plus 1 multiplied by 8. I think. No? Maybe not. Now it's being even weirder. Let's see. Because I starts at length, which is going to be 3, and it goes down till... Oh, I see. We have an extra number in here. So pointer plus equals 2, which points to the first value there. So this seems to be like length minus 1 or something. Okay. So what are all these add together? Does it equal something useful? 1205, 8624, plus 1280. Okay, this is already way too big. Somehow we went too far. So maybe these are backwards. Because let me think, if we start from the left and work our way to the right... Okay, I mean, it's the same thing. It's just backwards now. Doing this doesn't do anything because it just... There's no bits to shift. It's already at the end. Let me think here. Do length minus I, so these are inverted. Because we want the last one to be at the front. What is that? That's 50 million. That's not right either. There must be something I'm missing here when making this. Because... I guess when combining these place values together, if this was hexadecimal, you just mush them together, right? Like that. But if it's like decimal, what do you have to do? In decimal, you can't just... Can you just add them together? No, you have to do something to them. If these were in decimal, you'd have to do this to the 10th, I think, plus this to the 100th. So it'd be like... I'm just trying to understand the math behind it because these are like place values, right? So 5 to the 100th. Okay, that's definitely not what we're looking for. 100 to the 5th? That also doesn't look right. I think it's 10 to whatever place value we're at. So 10 to the... It'll be 10 to the 2nd. Multiplied by whatever your number is. I think. Or 10 to the 3rd? 2 seems kinda... small? Yeah, that doesn't sound right. Because this number would be larger than this number. But each of these is supposed to represent... I guess it's actually represented in hexadecimal. And that's what I'm missing here. Since they're in hexadecimal, each of these numbers need to be treated as such. So these numbers don't represent their numerical values. They represent combinations of hexadecimal numbers. So that means the first, this represents 1 to the 16th, right? Or 16 to the 1? Or is it 1 to the 16? I think it's 1 to the 16. The next one is 2 to the 16, and so on and so forth. So 1 to the 16 multiplied by whatever the value of it is. So in this case, D8 should represent 216, right? So then you have 216. Then you take the next place value, which is 2 to the 16th, and you multiply that. Oops. So 2 to the 16th. Multiply that by whatever value you have here, which is going to be 184. Okay, that doesn't sound right either. It's not 2 to the 16th, it's 16 squared multiplied by 184. And then your final number is 16 cubed multiplied by whatever your actual value is. Right? Kind of? That doesn't add up though, because now you have... Gosh, why is this so complicated? There must be something else I'm missing here. In binary, if we were to combine these, what would it look like? Let's see if we can figure out that conversion. So 5B8D8 is 0101 10111 where does this one come from? Oh wait, 111, right. Then 000, and then the final bit is 1101 1000. So it looks like you just mash all of these together and you get your result. So you don't do any addition, you just bit shift them over. No addition, just bit shift. So the algorithm then becomes, put in these numbers, bit shift them 8 to the left, put in the next set of numbers. Keep bit shifting until you're all done. So value will be equal to value bit shifted 8 left, and then you OR the next set of bits. Okay, let's give that a shot. Are we just not printing it out? Hello? Why did I comment that out? Okay. So for each step in value, what are we doing? Zero to 3, 3 to 773, 773 to negative 72. I think we have to convert this as well. No, that doesn't seem to matter. Oh, maybe we should convert this number too, huh? Convert this number? Okay. So we shift over, we ORed the new bits, and then we have to shift them again. Okay, that's starting to look like something. So we first bit shift and we get a 3. That doesn't sound right though. Is it because we're doing this? 1, 2, and 4. That should be 5. I feel like we're not... Oh, we're starting at this number. Why? Don't start at that number. Start at 1 after it. So then... Yeah, let's increase pointer by 1 after we get that value. There we go. Got it. Alright. So I was 1 off this whole time. So the first value is 5, then it shifts all that over. Oh, finally we were able to read that value. Well, now that we read it, it'll be easier to get stuff later on as well. Okay, so what we learned, I'm actually going to move the pointer increase out to here because I think that makes the function more generic. So increase pointer by 2 once we get to here. Should result in the same thing. Okay, so here's what happened. Here's how bit shifting works. You have, and what I was trying to figure out, we have these 3 bytes to combine together. When you're dealing with what bit twiddling, which is what we like to call it because we're messing with bits in binary. So we have, in this case, a series of 1s and 0s, right? Just, I wonder if this shows anything useful. I don't think it does. Okay, but you can see down here, it shows what the numbers represent binary are. So 5 is represented like this. I'm actually going to write them all out. Nope. And then you have 184, which is represented like this. And then you have 216, which is represented like this. So these are our 24 bits we're trying to combine together. And when you put this number together, you get the number 375,000, which is what we were looking for. So what we do here in our loop is our pointer is currently starting at this position here. So we have to read in that 5, which ends up being the 000101, right? So we have this number now. This is our final number, and that's equal to 5 at the moment. When we do a bit shift 8, what we're saying is all these bits we just made, push them over by 8 slots. So we push them over, and what we end up with are 8 more bits revealed in front of it. That makes the number go up to some really high number. In this case, I think it's going to push us into the thousands. I can check. 101 and then 1, 2, 3, 4, 5, 6, 7, 8. So yeah, it pushes us into 1280. So that's what happens when we bit shift by 8. Then we have to bring down read our next set of bits. So we read in the next set of data, which is, in this case, the decimal number 184 right here. And what we're going to do is take this number we have and OR them. So we're going to do an OR operation between these two. Now when you do an OR operation in binary, it's going to combine all the bits together. So because the place values for these are not equal, we have to substitute like empty values here. So just like if you were adding doing addition in base 10, you kind of do the same thing, right? If there's nothing there, you just add a bunch of placeholders. And that gives you a total value that looks something like this. That's what an OR does. An OR is just an addition. You can also do an AND. An AND would be like, check if they are both true, and if they are, then it returns true, otherwise it returns false. That's where we get the term AND gates from, AND logic. If both are true, it's on, otherwise it's off. We also have XOR, where only one can be true. If at least only one is true, it's on. If they're both true, it's off. Or if they're both off, it's also off. Anyways, we're only using OR logic here. So we end up with this. Now we're getting closer to our number we want. This is now the number 13 or 1464. We can check our output to confirm that. Oh wait, we deleted that. But it's basically these two numbers combined, 1280 plus 184. I think I did that math wrong, 1424, my bad. But either way, that's how we get that. Let me double check. I don't believe my math right now. 10110111000. 1464. I was right the first time. Alright. So now we have to do that bit shift by 8 again, and we'll end up with a much larger number because we're just adding 8 placeholders again. So when we do that, we end up with this number, 23,424. So the final part is to read the last piece right here, which is the number 216 in decimal. And we have to do an addition again. So again, because we have all these empty placeholder values, we have to fill them in like this and do our addition that way. And so we're going to do an OR operation again, or on this. And then we end up with this. And that is our final number. It should be our final number. 1011011110001101100, giving us a grand total of 375,000. So that is where we get that is how we get the tempo. So today seemed a little complicated. We're kind of getting familiar with the documentation here, and we're starting to read through this example file. So I think tomorrow we're going to be making a lot more progress because you can see we're going to be getting into reading notes. So hopefully that turns out well. We just need the tempo, we need the durations, like you see there's delta times here, and we need the notes, like what we're actually trying to play. And hopefully with all that in place, we might be able to produce a tune and read it next time. But we're going to have to do a lot more bit twiddling. This is the fun in doing binary. This is why I chose to do this kind of exercise for the next few days. This project will be pretty fun to get into. It's a very different exercise to work with binary or bits. It's not something you get to do very often and every day. We also had to do this little thing because apparently they get turned into 2's complements, which means they are signed and not unsigned. And so because of that, I had to do this little conversion. This is a shortcut to turning it into an unsigned byte. We might make a function for that later to save it. Anyways, for those of you that tuned in today, thanks for watching. Hope you enjoyed. We went pretty long today to get started here, but we're going to be doing a lot more tomorrow, hopefully, now that we kind of have a system started. So thanks for watching, everyone. Have a good one.